Welcome to the Foundry by Forge College. I'm your host. Today, we're drafting the engineering blueprint for our explainer on dApp architecture overview because, let's be honest here, just throwing isolated pieces of Web3 code together and crossing your fingers? Yeah, that's a recipe for a very expensive headache. As part of our module on implementing dApps with Solana Web3.js, we're going to take all those isolated pieces you've been learning and assemble them into a beautifully functioning, highly resilient machine.
All right, here is our schematic for today. We're going to cover the architecture blueprint, inspect the JSON RPC engine, figure out how to build resilient reads, map out the entire communication pipeline, lock down our core engineering principles, and finally, prep our next steps for assembly.
Section 1. The Architecture Blueprint. This is where we bridge error logs to the actual app flow. Now, in our previous lesson on error handling and security awareness in transactions, we looked at how to diagnose failures. But to really master dApp development, you've got to know exactly where those failure checks actually belong in the grand scheme of things.
The big takeaway here is making the leap from merely reading transaction-level logs, diagnosing those angry red runtime errors from your command line interface, to actively designing an application-level flow where those diagnostics and retries actually live. Think of it like the difference between just staring at a broken gear on your workbench and designing a whole engine that doesn't explode the second it hits a pothole. We want your UI, the user's wallet, and the RPC to interact so smoothly and predictably that your users aren't left rage-clicking their screens. Moving on to Section 2, the JSON RPC engine, diving into the mechanics of the request. Let's inspect the specific gear driving our data. This right here is the mechanical heart connecting our front-end application straight to the Solana blockchain.
Let's break down the exact anatomy of a request. Your Web3.js connection basically wraps these fields up to act as the requester, while the RPC node responds. You've got your method, which tells the node exactly what you want it to do, like, say, fetching a balance. Then you've got your params, which act as the specific instructions. The ID is basically a tracking number your client uses to keep things organized. And finally, the result or error that the node hands back to you. It's this precise, mechanical exchange of data, and genuinely understanding these parts is exactly how you take total control of your network communication. All right, Section 3, building resilient reads or testing our structural integrity. With the engine mapped out, we absolutely have to test its integrity by building resilient reads directly into the front end itself.
Because let's face it, networks hiccup all the time. It's just a fact of life. So instead of panicking when a fetch hits a 500 status code or simply times out, our system quietly kicks in and switches over to a backup RPC endpoint. Then it saves the diagnostic data. This means if all else fails, we can tell the user exactly what went wrong instead of just throwing up a terrifying blank screen and leaving them completely in the dark.
Section 4, the communication pipeline, essentially our assembly line. Let's zoom out a bit and map this out across the entire 6-step assembly line of front-end, wallet, and RPC communication. This is the moment where all those isolated gears finally start turning together.
Boom! 0 milliseconds. The user clicks, and we instantly update the UI optimistically. By 100 milliseconds, we are fast fetching the required state from the RPC. At 500, we're knocking on the wallet store for a signature. Once that's signed, at around 2000 milliseconds, we submit it to the RPC and grab our receipt ID. Hitting 4000 milliseconds, we're securely polling for confirmation, and finally, by 4500 milliseconds, we clean up the whole process and record our analytics. It is a beautifully orchestrated sequence that keeps the user engaged rather than trapping them in some infinite spinning loading screen of doom.
Now, to make sure we don't completely lose track of our users' actions during this rapid-fire timeline, we rely on something called a correlation ID. Think of it exactly like a coat check ticket at a busy club. You hand over your jacket, you get a number, and you go dance. Because we're dealing with asynchronous events, waiting on networks, waiting on users to actually click approve, this code check ticket ensures that when a response finally comes back from the blockchain, our app knows exactly which optimistic UI update it needs to finalize, or if things went south, revert.
And here is the golden rule. I really want to emphasize this because it's the most critical safety feature of this entire machine. You absolutely must verify the state, things like balances and accounts, before you ever prompt the overly cautious bouncer, which is the user's wallet, for a signature. Nothing, and I mean nothing, is more painful for a user than paying a network gas fee to approve a transaction, only to find out they didn't even have the right token balance to complete the action in the first place. Read the state first, validate it, and only then ask for the signature.
Section 5, core engineering principles. This is all about securing the schematic.
As we begin to wrap up our drafting session today, let's distill everything down to our core engineering principles. These are essentially the load-bearing pillars of your entire architecture. By rigorously stamping these 4 rules into your workflow, you'll eliminate nasty race conditions and transform those messy error logs into UI messages that actually make sense to a human being. First, enforce that reads before sign rule we just talked about. Second, wrap all your RPC calls with explicit retry logic and diagnostic metadata. Third, treat the wallet strictly as a signing boundary. It doesn't handle your app's logic, it just securely signs things. And finally, preserve those correlation IDs so your UI never loses its mind midway through a process.
Section 6. Next steps and assembly. Preparing for your integration code. We have our blueprint. We've laid out the theory and we've successfully mapped all the connections. Now it is time to look ahead to the actual code. This conceptual foundation guarantees that when you write your Web3.js integration code in the next lesson, you are going to know exactly where to attach your logic. You're no longer just blindly guessing where a try-catch block should go. You are moving from pure theory to absolute control. You know exactly where the UI intent starts, where the RPC acts, and exactly where the wallet steps in.
So, let me leave you with this thought. If you don't build this kind of safety net into your architecture from day one, are you really building a resilient dApp? Or are you just building a ticking time bomb for your users' wallets? Really think about that. Thank you so much for exploring this blueprint with me today. To continue building your Web3 engineering skills and to dive deeper into this subject and other Web3 topics, make sure you head over to forge.college. Grab your tools, keep following the schematics, and I'll see you in the next explainer.